This is Math 156, calculus using Maple. And what I'm going to do is go over the second exam that was given on Wednesday, November 18th. You'll see the Maple worksheet here, and I'll just say a few words about each problem, and then I will save the worksheet and post it to the Blackboard website. So problem 1 was to compute 3 integrals. The first is this indefinite integral, arctangent of x cubed over 1 plus x squared. This is the answer. If we make this a definite integral from 0 to 1, this is the value, pi to the 4th over 1024 exactly. And if for some reason we want it as a decimal, we can evaluate this and we get this number. Alternatively, we could have written the following. I could have just written EVALF here. And then what I get is the integral evaluated precisely, or the integral evaluated as a decimal. And similarly, I asked for the integral from 2 to infinity. This is what it is. And again, if I want it as a decimal, I can just put EVALF, evaluating floating point there. And here I get the answer as a decimal. Problem 2 is to consider the function. Oh, let me just make one other point. When you go from one problem to another, you want to make sure that you haven't stored anything in memory which might mess you up later. So I can go back and click on this symbol here on the top, which it's the restart Maple server symbol, which just clears anything from memory. Okay, so here I have my function. It's this 4th degree polynomial. I always like to see what they look like. I adjust the x and the y's to make sure I can really see it properly. I want to just point out that if I had just written x, it would graph this function from -10 to 10, and you don't see what's going on in here. So it was better, you play around, and then you see that with this choice of range of values for the plot, you actually get a very nice idea what the graph looks like. So you know immediately there's a local minimum, a local maximum, a local minimum. This is concave up, concave down, concave up. So you know by looking at the graph a huge amount about what it looks like. The x-intercepts are where the graph crosses the x-axis. Those are the points where f of x equals 0. If you solve for them, this is what you get. The y-intercept is just the value of the function at 0. That's the y-intercept. Now, if you want to find the local maxima and local minima, the first thing you look for are the critical numbers. Those are the points where the derivative is 0. This is the derivative. So if you solve the equation, derivative equals 0, you get 2 critical numbers, -2 and plus 2.75. And 0, 3 critical numbers. They have to be 3 because they're 3. And if you evaluate the second derivative at each of these points, so critical point, you see there are 3 numbers that show up. And they're labeled as follows. If I write critical point, square bracket 1, I get the first of them. If I write critical point square bracket 2, I get the second. If I type critical point square bracket 3, I get the third. So critical point square brackets 1, 2, or 3 goes through these three numbers. And for each of them, from writing this as a loop, I could also just write it out. For n from 1 to 3, I'm evaluating the second derivative. And what do I see? I see that the second derivative is positive at -2 and 2.75. So you have, by the second derivative, if this test, if the second derivative is positive, you have a local minimum. At 0, the second derivative is negative, so you have a local maximum at 0. Where is the function increasing and where is it decreasing? It's increasing where the derivative is positive. So I can use the solve command to work out an inequality. Solve, where is the derivative positive? From -2 to 0, or from 11/4 to infinity, or if you like this as a decimal, from -2 to 0 and 2.75 to infinity. So where it's positive, the function is increasing on these intervals. Here is where it's negative, and the function is decreasing on these intervals. Again, if you look at the picture, you see decreasing there, decreasing there, increasing here, increasing there. What else do we need to find? We need to find where the function is concave up, concave down, and where are the inflection points. Here we're solving the inequality for the second derivative being positive. Where the second derivative is positive, the function is concave up. Here we're solving where the second derivative is negative on those intervals. The function is concave down. And the points of inflection are at the 2 points where you change concavity from up to down and from down to up. That's problem 2. In problem 3, we want to plot these two curves, e to the x plus e to the minus x over 2, and this upside down parabola, that's my function g of x. And when you plot them, this is what they look like. Again, you have to choose the right range of values for x in order to see what's going on. If you just plot this, x, it'll plot from -10 to 10. You see what's happening. It's nicer to blow it up a little bit and see it more clearly. So I just chose to do that. But so long as the graph is okay, graph is fine. Where do the points intersect? Where f of x equals g of x. Now, here's a very important point. If I just write, solve the equation f of x equals g of x, it gives us this 1 point around 1.9. But you can see from the graph, there's another point of intersection. And how do we get Maple to give us that? Well, you can say, this point here where it's negative, it's not coming up, but I can force Maple to look in a negative region. I can say, instead of just writing comma x, I write x equals -4 dot dot 0. That means look for a 0 between -4 and the origin. And when I do that, I get -2.86. And when I just ask without putting a limit on a restriction on the range of values of x, I get b. So these are the 2 points of intersection. And I know from calculus that the area between two curves, if it's simply one curve intersecting another, one above the other, it's the integral of the top minus the bottom. So this is the integral of g of x minus f of x. That's the area, and this is what it's equal to. I could, I guess, just from the point of view of Let's try this. If I write this with a capital I and a lowercase I, then I get this written out explicitly. This is the top curve. This is the bottom curve. This is actually what the integral is. And when it's evaluated, you get this number. For problem 4, we have a curve given by this equation, x times the sine of pi x plus 8x squared y cubed equals 6. We want to prove that a certain point satisfies the equation. That means if we substitute in the value x equal 2, y equal a half, we should get 6. And the command to substitute is subs for substitute. X equal 2, y equal a half, you put those first, and you're substituting those values into C, and when you do, you see you get 6. So that shows you, that proves that the point we want to show that the point 2 comma a half, I'll just write it as 0.5, lies on the curve C. And here's how you do it. Just substitute in these coordinates, these values for x and y, and you get a 6. So it does lie on the curve C. Now, to find the derivative, well, to find the slope of the tangent line to the curve at a point is just the value of the derivative. So the way you find the derivative is by implicit differentiation. That's what you learned in Calc 1. The command for implicit differentiation is implicit diff. By the way, if you weren't sure about that, let's see. Get this out of the way. If I go to help, Maple help, if I were to type in implicit differentiation, let's see what happens. And what I see here is there is the command implicit diff. And this tells you how to use the command. You have a function involving x and y, or an equation, and you want to find the derivative of y with respect to x. So here we have this equation involving x and y. Y is defined implicitly as a function of x. Implicit diff of this equation, y comma x, this is the derivative. And we want to evaluate the derivative at the point x equal 2, y equal a half. So you substitute x equal 2, y equal a half into this, what I called ID for implicit derivative. And this is what you get, this number. And as a decimal, it's equal to this. So that is the slope of the tangent line to the curve. Once you know the slope of the tangent line to a curve at a point, you know the tangent line. It's the slope. This is just the point slope formula. Mx minus times x minus 2 plus a half. So this is the tangent line. And you want to plot this, so you have to open the plots package with plots, and you use the implicit plot command. And what we're plotting is this tangent line together with the curve, and this is what we get. Here's the beautiful picture of what's going on. The curve Here's the 0.2 comma a half, and that's the tangent line. Very nice. Problem 5, this is a problem just like a couple of problems on the review sheet. We have a sequence of numbers, an. An is the nth, 3 times the nth root of 2 minus the nth root of 7. So for example, if you want to know what is the value of this when n equals 100, that's just a of 100. And if you want, so let me just, I've written this as function. That's a of 100. 3 times 2 to the 100th minus 7 to the 100th. But if you want to know that as a decimal, so you actually have some idea about how big it is, you do EVALF. And this number is a little bit bigger than 2. And if you're curious, not curious, you're told to compute the limit of this sequence as n goes to infinity. This is what it is now. Let me just do this. Yeah, I cleared the memory just to, and now I get the end. This is 2. This limit is 2. I could also, just to make this a little bit clearer, let me see what happens. I write it like this. Oh yeah. So the limit is 2. Now, I want to find the largest n where an is less than 2. So I can just do some experiments. I want to do a loop for each n, let's say from, I don't know, 1 to 20. Let's see what happens. Compute this. These are the sequence of numbers. And I want to know what's the largest n for which is less than 2. Well, right here. When n is equal to 9, it's less than 2. When n is bigger than 9, 10 or greater, it's above 2. So this is less than 2. The largest number is 9. And just so I don't have to see all this stuff on the screen, I just made this, I think, let's say from 7 to 10. So the answer is 9. Right? The largest n is n equal 9. Now I want to find the largest n, but see, after that, n is bigger, an is bigger than 2, but it's approaching 2 as a limit. And I want to find the largest n. Oops. So I want to find the n when these numbers, let me just, for example, let's go from 100 to 200. Oh, and from 100 to 200. All right, so I'm doing this huge calculation. Maple can do it very quickly. these numbers are decreasing, and I should have said I want to find the smallest n from this. Once it gets over 10, the smallest n for which you get a number less than 2.003. See, 2.0, see, these are much bigger. These are decreasing, but it's like, this is still 2.0006. I want less than 2.0003. So let's say I wanted to go up to 1,000, but just to get an idea, I don't want to look at all 1,900 numbers. Let's go up by hundreds. So I can say for n from 100 by 100, this means I want to go 100, 200, and so forth. So let's see what we get. 100, 200. When do we get something less than 2.0003? It's like in here. See, at 400, it's 2.00032. At 500, it's 0.00026. So we really want to look for something between 400 and 500. So let's just say I go by tens. And here, see, so when do I drop below 2.003? It's something between 430 and 440. So let me just look at the numbers from 430 to 440. I don't have to go up by tens, I can just go up by ones. Here we are. It drops below 2.003. This first time, the smallest number for which that's true is 437. Sorry. No, I just state the problem correctly. So the largest n for which an is less than 2.003 sorry, it should be the largest n for which this number is bigger than 2.003. That's what I should have said. So let me just correct this here. The largest n for which a of n is greater than 2.0003. So the answer is 436, because when you get to 437, you're less than 2.0003. So the answer is n equals 436. And let's see, this is an alternate way of doing it, but let me get rid of that because it's just, okay. There we are. Okay, that's the exam. Because part D of 5 wasn't stated properly in the exam, everyone will get full credit for that piece of that part of problem 5. Okay, that's it. Everyone, we're done.